Hello, Science 10, and welcome to chemical reactions. This is the first part of a long kind of couple lessons about the different versions of chemical reactions and how that works. Today, we're going to be looking at the evidence of chemical reactions and change, which is part of lesson 11, just after water. So the goal today is to talk about the differences about what is a chemical reaction. How do we set that up? So a chemical reaction is when we mix two substances and the change happens that forms a new substance. All right. So for example, if we think of rust on a car, rust on a car is because iron has been exposed to oxygen and then it makes a new compound called iron oxide or rust. That's an example of a chemical change. All right. When your full food in your pantry or in your fridge starts to mold, that's also a chemical change. So what we have to understand is that there are two parts to a chemical reaction. There's the reactants, which are the parts that are involved in the chemical reaction. And when we write a chemical equation, they're found on the left side of the chemical equation. And then there are the products, which are found on the right side of the equation. And they are what are formed in a chemical reaction. So when we were to look at writing an actual chemical equation, it's reactants, then the arrow, and then products. Now, you have to remember that there's not always going to be two reactants and two products. Sometimes they're different. But what you do have to remember is that plus signs are used to separate different compounds. So reactant A and reactant B are separated by plus signs, and product A and product B are separated by a plus sign. And when we're trying to separate reactants from products, it is an arrow in the direction moving from reactant to product. So this indicates that a reaction has taken place. So what are we talking about when we talk about chemical reactions? Back in grade 9, we talked about physical and chemical change. We talked about how physical change could be something like cutting your hair or trimming a plant or taking a bite out of a hamburger or breaking glass. It doesn't change the actual structure that you have or the compound you have. It just breaks it into smaller pieces. Things like dissolving, state changes, moving from liquids to solids and solids to gases and stuff like that. Those are all physical changes. Water is still water if it goes from ice to liquid, liquid to gas. It's still H2O. But a chemical reaction is different. A chemical reaction will give us a couple different pieces of evidence that we can see that shows that a change has occurred. So the first one is all chemical reactions involve some sort of change of energy. So when we talk about a change of energy, we're either talking about a temperature change, so something gets hotter, okay, so thermal energy, an emission of light, that means light energy, so something might start on a fire, explode, and give this bright light. You might hear it, or it might start an electrical energy. So it might be the conversion of the chemicals inside a battery to energy passing through the wires. So that's one piece of evidence that shows us that a chemical reaction has occurred. Another one is if there is an odor present. So whatever you're making, okay, starts off as one thing and then produces an odor afterwards. That's an example of a chemical change. Example would be baking cookies, making a cake. When you are mixing the batter or your cookies or your cake, it has a nice smell, but it doesn't have a smell. But then as you bake it and add heat and change it, you get an odor change. Another big one is color change. Okay. When a product starts off as one color and then or a reactant starts off as one color and then the product is a whole different color, okay, from the two original or one original thing, that is also an indicator of a chemical reaction. Another one, which I'm a big fan of, is bubbles in solutions, so gaseous products. So we do a lot of this with photosynthesis when we're talking about cellular respiration and photosynthesis. We do a little activity, you get to see the bubbles actually being produced. A bubble being produced or gas in water, in solution, is also another indicator. We already talked about precipitates because we've talked about solubility, but precipitates is a way of forming a solid when you mix two liquids. It can change color, it can be cloudy, it can appear thicker, but essentially if you form a solid, into liquids, you know there's been a chemical change. Let's just quickly go through what a precipitate is again. So a precipitate is a solid product that happens because takes place inside a solution, okay? We have to remember that not all ionic compounds are going to be soluble. Even though we use it as an indicator that it is an ionic compound, not all of them are. And if you have an ionic compound that isn't soluble, it means it's forming a precipitate. So when we look at it, we want to talk about how do we figure out if something is a precipitate or not. So this occurs because your positives and negatives in solution react to cause an ionic compound that doesn't mix in. So in the example above, NaOH plus copper 2 chloride gives us sodium and copper hydroxide, copper 2 hydroxide. What we are seeing in the picture is the copper 2 hydroxide is not soluble, so it becomes a solid within the liquid. We can figure out solubility by using the data sheet we have. It's called the precipitate chart. And the precipitate chart tells us if something is high solubility, which is aqueous, or low solubility, which means it's a precipitate. So this is the chart. And again, when we're talking about solubility, we're talking about solids and aqueous, not solids and liquids. So aqueous just means that it mixes into water, okay? So the solubility chart can be used for two reasons: to see if an ionic compound will dissolve when placed in water, and to find out if a precipitate is formed when more than one ionic compound is mixed in solution. So what we want to do is we want to check to see which ones have low solubility and which ones will create a precipitate. So what you are going to do is you have the rest, okay? Using the precipitate chart. Step one is you find the metal for the ionic compound at the top, or sorry, the non-metal for the ionic compound at the top. Then you find the metal in the columns below, and then you check to see if they have high solubility or low solubility. Reminding yourself, high solubility will always be aqueous, and low solubility will always be solid. All right, so thank you, and if you have any questions, please let me know.